Well, good morning. Why don't we get started? My name is Ed Blucher. I'm the director of the Enrico Fermi Institute, and I'm thrilled to see all of you here in person to start the 91st Compton Lecture Series. As probably many of you know, we haven't had one of these lectures since the fall of 2019. So it's been a long gap, and we're thrilled to see all of you here, especially in this building, which is the new home of the Enrico Fermi Institute. These lectures began in the winter of 1976. So they've been going on a long time, and the speakers have been a whole series of, they're all given by outstanding young researchers who are here, many of whom have become very well-known senior researchers over that period. So my only job today is to introduce our speaker for the series you'll have for the next 8 weeks. So our speaker is Seth Koren. He was an undergraduate at the University of Pennsylvania, did his graduate work in Santa Barbara, and then came here as an Enrico Fermi Institute UMA Fellow in 2020, the summer of 2020. And he's going to be speaking to you about very modest scope, particles, the cosmos, and you, an origin story from the edges of space and time. So I hope you'll all enjoy the lectures. And again, we're very happy to see all of you here in person. So Seth.
Everyone, thank you for coming, and thank you, Ed, for the kind introduction. I'm honored to be given this opportunity to give these lectures. It's quite a unique opportunity, so much so that there isn't really much guidance on what I should do with the lectures. And so I thought with the first one, let me see what I should, I thought with the first one, I take it, rather than giving the first part today of some 8-part story, I take today to explain in overview what I'm going to tell you, to very briefly, quickly zoom down from human scales to the shortest scales that we currently understand, and very quickly tell your history since a few minutes after the Big Bang, all things that I will go into more detail on over the next 8 weeks. And also to tell you why I've decided to go in this direction, give some motivations for the topic I'm going to be talking about, because as I said in the title, in some sense this is going to be about all of our origins. The origins of this lecture series are with me and my own origins, so I thought there might be some interest in some biographical background information, and also it would be a good disclaimer of my own background and the perspective I bring to this topic. So a little bit more detail than Ed gave. My educational biography, in brief, I was I grew up around Philadelphia, and I went as an undergraduate to the University of Pennsylvania. I got my bachelor's degree in physics and in math, and I was very fortunate to work with a brilliant astrophysicist, Professor Cullen Blake. We thought together about stars and exoplanets. I did some work on asteroids. And as an undergraduate, I found, when I was learning physics for the first time, I found myself increasingly interested in quantum mechanics and in particle physics and cosmology. And so I decided to, after I graduated from Penn, for my PhD work, to go cross-country to the University of California, Santa Barbara, to work with my advisor, an eminent young particle theorist, Professor Nathaniel Craig, and we did lots of things together. I'll say a bunch of words, just because some of them will come up later on, but don't worry about not understanding them right now. But we did work on the cosmology of some models known as twin Higgs models. We did lots of collider phenomenology, understanding what we might see at the Large Hadron Collider, exotic signatures. I did some more formal work in amplitudes. We wrote papers on all sorts of model building, understanding what the world looked like on very small scales, about dark matter, neutrinos. The central part of my thesis work was work I did with my advisor on the hierarchy problem, which is some deep theoretical puzzle about the Higgs boson. And we proposed some novel explanations for it. I wrote my dissertation on that topic, and it was kindly given the American Physical Society's 2022 Sakurai Dissertation Award for a dissertation by a theoretical particle physicist. And in 2020, I came here as an fellow. I'm continued to think about a broad variety of things, lots of interest in symmetries, in understanding the stability of the proton, some cosmological issues associated with the early universe. Recently, I've been working with a string theorist here to try to take some mathematical technology and make use of it in particle physics. That's been a very interesting program that I'm excited about. And this is my final year as an fellow. Next year I haven't put it on here, next year I'll be at Notre Dame as another postdoctoral position, not too far away. Now, so this, in very brief terms, is my CV, and given this CV, if I were someone else, or maybe if this were before the pandemic, I might have given a series of lectures called something like The History of the Universe. I've done lots of work from different angles on the Higgs boson. This is the final piece of the standard model that we discovered about a decade ago. It's still very exciting. There's, even though this is some specialized topic, there's lots to say about its predictions, how we actually found it, different puzzles it could be involved in, how it might be related to things like dark matter. So I might have given some very specialized series of lectures, but as you've seen, that's not the direction I decided to go with this. And the reasoning, or what's behind that, in some sense, is that on the previous slide, I only gave you some part of my intellectual history, and there's another important component to it, which I'll tell you about in brief. I was really raised in opposition to science. My parents understood the world in a very pre-scientific way. They weren't. They were content to just sort of describe the world and not try to understand how it works. And in particular, it pains me to say, but my parents throughout my life have been prominent producers of scientific medical misinformation. And in particular, anti-vaccine misinformation, which has been I was really raised in a very different way of thinking about the universe than what I'll tell you I've learned today and in these lectures. And to my shame, I only started seriously questioning the point of view, the beliefs of my parents, the way I was raised to understand the universe, when in my teenage years I became seriously ill, mysteriously ill. We, as a family, we didn't see medical doctors ever. That wasn't the way we thought about the universe. My parents believed that as humans we were created as some singular perfect entities, and any intervention like medicine or like chemicals or something was necessarily something harmful. But I fell ill as a teenager, and no visits to chiropractors or acupuncturists or homeopaths or astrologers, tarot cards, pilgrimage, healing crystals or lasers or magnets, which all things we really, all interventions that my parents were happy to try. None of these did anything. It was only after many years of begging my parents that I saw a medical doctor for the first time in my life shortly before I turned 18, who very easily, promptly diagnosed me with having 2 brain tumors.
Oh my God.
I'm fine now. Perhaps more accurately, I should say, don't worry, the brain tumors are gone. Maybe I'm fine is a slightly higher bar. But it's important to me that I say that after spending years questioning the way I was raised to think about the world and trying to understand how the universe worked in a more scientific way, coming to this realization that science works quite well myself. I, of course, spent many years trying to convince my parents, likewise, to think more critically about the way they thought about the world, to try to prevent the clear and present harm that I saw their actions doing. Unfortunately, I eventually concluded I could not change their minds, and I felt morally obligated to take the strongest stance I possibly could against their beliefs, their actions, by cutting them off in protest in 2015. And unfortunately, you know this last bullet point already, that over the past years there has been a pandemic which has had these central issues of my childhood of medical scientific misinformation as the key issues of the international stage. This has been a very difficult period for me. I'm sure it's been very difficult for many of you. I certainly have despaired that despite my best efforts in trying to prevent the harm I saw in my parents' beliefs, my actions alone could not prevent, indeed, the terrible excess deaths of the pandemic caused by vaccine hesitancy. Although I believe, certainly I slowed my parents down. And was there one more thing I wanted to say? And good. And in particular, the pandemic coming here, I moved here in 2020 and promptly spent a full year in isolation downtown in my apartment by myself, so it gave me a lot of opportunity to think about the world, to re-understand my own past, just how much the serious brain damage I went through had affected me, but also think more about the world and some broader picture of it. And that's the spirit in which I've planned to give these lectures. I think the last years have really re-emphasized to me that it's quite important, really to all of us, to understand how the world works in some sort of scientific way, that our beliefs about what's fundamentally going on are not just some abstract thing, but really do affect decisions we make personally and on a societal level. So my plan is to, rather than going into some very specialized topic, to give a broader introduction to particle physics and cosmology, and to try to connect a bit with who we are as humans. So the strategy that we're going to employ to understand the world, based on a few philosophical pillars, first and foremost being empiricism, that we want to understand the world firstly by carefully observing it and making precise observations of of what is happening, and trying to come up with theories of what's going on. This is as opposed to taking as our primary source some oral history or what we see when we take some psychedelic drugs, but rather to look out at careful observations of the world. And our strategy for understanding it is going to rely on the idea of mechanism, that in fact there are explanations for everything that we see going on. A priori, you might have thought that there weren't. This is the way my parents understood, and I was raised to understand the world. It's just things that happen, we could describe them, but fundamentally these weren't things that we could understand. But in fact, this has been an incredibly good strategy. We've learned that we have been able to understand very precisely how things work. And that precise understanding has come through the strategy of reductionism. That these explanations, the best way to explain the world, how something works, is by looking at it on very small scales, by looking at its subcomponents to figure out how some larger body operates, and to understand what's happening today by understanding what happened in the past at earlier times. And again, we'll see this strategy has worked extremely well, even though a priori you might have said it didn't need to. And I hope to also emphasize that while the world around us on human scales is very complicated, what this strategy, the success of this strategy has revealed is that if you look at very small distances at very early times, there is some fundamental simplicity, and all of the complication today, all of the complication that we see on our scales comes as some emergent property when we look at larger scales and longer times. So first, I want to zoom in down to the smallest scales that we can probe. I want to ask what we're made of. And let me quickly say that this is a very old question, not just a question that you and your grandparents and their grandparents have asked, far older, as to how long exactly we've been asking what we are in some fundamental way. Okay, I can't tell you an exact date. As an upper bound, you might take that we believe now language began more than 1 million or so years ago with Homo erectus. We know that Homo erectus, our ancestors over 1 million years ago, were living in groups, they were making tools, they were hunting, they were cooking. It's believed that they had some notion of language. As to some more direct evidence for maybe a lower bound on when people were asking these sorts of existential questions, we have evidence of burials in the Middle East, in Africa, more than 100,000 years ago, both of Homo sapiens and Neanderthals, leaving grave goods, burying their venerated dead with decorations. Clearly, these were peoples who were thinking abstractly about themselves, who were attaching meaning to each other, and who were asking questions like, what the heck is going on? So a very, very old question, but one that only a few hundred years ago, in the 1600s, when we devised, first Van Leeuwenhoek devised a microscope to allow us to look at very small scales and actually make some precise observations. Only then did we understand the very basic fact that all of us are made out of cells. We are not some singular entities, but in fact, we have subcomponents of our own. Here's a drawing of one of Hooke's early microscopes, and a drawing he made of some cork cells. Good. Is this too much light on the front? Yeah, okay. That was some, when you came in, some light changed. No, not your fault. Do you know how we turn off these? Well, no, I think it's probably one of these. Okay, there might also, wait, hold on.
Now we're getting fancy.
Okay, all right, hopefully that hasn't impacted your view out the window. Wonderful, thank you. Okay, only, compared to how long our ancestors have been asking this question of who we are, it's only incredibly recently that we've understood the basic fact that we ourselves are made out of some subcomponents, some cells. In fact, you are some you as an entity are some emergent phenomenon out of trillions of cells that make up your body. And our cells are quite specialized. We have lots of different types, just a few for reference. This is now, we're zooming down to scales, something like a tenth or a hundredth of a millimeter. You're some collection of trillions of cells that work together to make the individual that is you. And we can understand lots of biology now over the past decades in terms of cells and the interactions between them that create you. But there's still an enormous amount of complexity at this stage. It's very hard to understand everything. They're making enormous progress, but there's much we have to learn. If we look even closer, then we find that cells are made out of molecules, as, of course, is everything. The air in this room is some mix of oxygen, nitrogen, carbon dioxide, water vapor. Rocks are some crystals, plastics, some special molecules that we've learned how to create. And our cells themselves are very complicated entities that are made out of proteins doing lots of very specialized functions. I have a close-up here of a cell membrane. This is, of course, one of the basic things that life has to invent to separate self and not self. Some fantastically complex proteins that make up the linings of every one of our cells. I've zoomed in here on DNA, which, of course, another very special structure that allows some self-replication of all of our cells. And again, over the past decades, we've learned an enormous amount about what our bodies, our cells look like in terms of these proteins and understanding the world at this very deep level. But again, things at this level are still very complicated. But if we zoom in even further, down to things like distances of a nanometer or fractions thereof, we find that molecules were made out of atoms. In the 1800s, chemists were beginning to understand that they could understand reactions, chemical reactions that take place in the world by some transmutation of atoms, combustion here, burning things, respiration, and photosynthesis. All of these have clear, simple explanations in terms of chemical processes going on at lengths of something like a nanometer. And in the 1800s, people began to see that there were some organizing principles going on. I have here Mendeleev's periodic table of the elements. He was able to finally arrange in a relatively simple way the enormous complication of all of these different materials, all of the different things we see going on in terms of properties of the fundamental atoms that make up those chemicals, those molecules. This nice chart color codes how much of our own bodies are made out of different ones of these atoms. We have lots of hydrogen, the lightest element, lots also of some of the other light elements, carbon, nitrogen, oxygen, but in fact our bodies require traces of some of these heavier elements as well, phosphorus, calcium, potassium. But nonetheless, we could see finally that there was some sort of structure going on, some sort of organization in how all matter works. Later into the 1800s, toward the end of the 1800s, we learned that we could zoom in even further. Now, zooming in at these scales, I have to disclaim I'm using metaphorically. We can no longer just take a more powerful microscope to look at even smaller distances. What we have to rely on are scattering experiments, setting up some configuration of some elements, some materials that are going to interact, and inferring from that what what things look like on very small scales. And we find that these atoms themselves, and we saw we had many different ones of them, but we find they're not just each some entirely separate sort of material. They're not singular objects at all. They contain, in fact, both positively and negatively charged components. In 1897, Thomson did this famous cathode ray experiment where he produced electrons from some atoms, was able to strip electrons off of atoms, and then see some classical scattering of a beam of electrons in a background electric field to infer that there were negatively charged subcomponents of atoms, subatomic particles that we call electrons, that can be stripped off of the atoms. Then, about a decade later, we carried out experiments suggested by Rutherford to find that the positive components of the atom, the nucleus, and each nucleus, each different type of atom has a different positive charge. Rutherford found by shooting helium nuclei at gold foil that the positive parts of the atom are in fact centralized, located in some central region of the atom compared to a much larger electron cloud in which they sit. In the decades following that, we were able to understand the structure of atoms, their chemical properties, using the theory of quantum electrodynamics, the quantum theory of light and photons, and indeed, you should think of an atom like carbon as having a centralized positively charged nucleus, a cloud of electrons around it, and they're all held together by the electromagnetic force. Of course, this is all stuff that we'll go into more in the following weeks. If we zoom in even further, we find that not only are the negative and positive charges of the atom different things, but we can explain why there are all of these different sorts of atoms. You see all of these nuclei with different positive charges in terms of each nucleus being composed of different numbers of individual just two particles, protons and neutrons. Protons carry the positive charge, neutrons are neutral. Our carbon nucleus that we were looking at contains 6 protons and, in that example, 8 neutrons. And you can understand now just from these two particles all of the properties of all of the different elements, the nuclei that we saw. The different number of protons controls the positive charge of the nucleus, leads to different chemical properties. The different numbers of neutrons leads to the phenomenon of different isotopes of elements. If you've heard of that, we understand now very well how nuclear physics works. And if we zoom in even farther, what we understood only in the 1970s by scattering experiments, now using electrons to probe the insides of protons and neutrons, we found that these nucleons, these neutrons and protons themselves, are not singular objects either, but are held together, are bound states of particles known as quarks, up and down type quarks that are held together by gluons, another type of massless particle, just like we found that the atoms are some composite particles, some bound states of positive and negative charges held together by photons. At a deeper level, the protons and neutrons themselves are bound states of quarks that are held together by gluons. The way this works is unlike chemistry, which has some classical properties. The way this works is now fundamentally quantum mechanical. There are new sorts of phenomena that lead to having these bound states when we look even closer. I should have said in words, this is down at something like 10 to the minus 15 meters. And if we look at even smaller distances, there are new, heavier, unstable particles. We can understand the phenomenon of nuclear decay by the exchange of some massive particles known as W bosons, which quantum mechanics allows to exist only on very short timescales. They're not stable themselves, so things aren't made out of them. And they cause neutrons to decay into protons and produce electrons and neutrinos. And finally, when we go to the LHC, we build these fantastic, enormous super colliders. We're able to probe distances at the smallest possible current possible scales down to something like 10 to the minus 18, minus 19 meters. We find that these W bosons get masses by interacting with this most recent particle we found, the Higgs boson. The Higgs boson, this is the most recent particle we found about 10 years ago at the LHC. And we can understand all of the properties of all of the matter that we've observed at the smallest scales in what's known as the standard model of particle physics. It contains quarks that make up the neutron and the proton. It contains electrons and neutrinos, the particles, the bosons that provide those forces, explaining why we have these bound states. Finally, the Higgs boson, this last thing that we've discovered. We'll go into all of this in more detail. It contains some surprises for us as professional particle physicists, but we have this incredibly compact, simple accounting for all of the matter that exists in you throughout the world, all of its interactions. We've understood things incredibly precisely, and we find that the rules at this smallest scale are in fact incredibly simple. We can understand very precisely everything that goes on. And it really amazes me that we are all made out of this same stuff. When you learn about this in particle physics textbooks, it's all treated very abstractly. Some experiments going on to understand the structure of matter at the LHC, but of course we are all made of this same matter. And telling the story I've briefly gone through today in reverse. Indeed, there are remarkable emergent behaviors as we look at longer length scales, as we look at longer time scales, the development and the how all of our cells work is of course incredible. But there's no magic going on. We can understand all of these behaviors continually better and better from the fundamentals of how matter works at its smallest scales, and we can understand how these complex phenomena come to be. Now, of course, that's how everything works today, but there's another important question, which is how everything we see around us got this way. What is the history of everything? So let me turn to that. So again, some age-old question like where we came from. It's intriguing, poetic that indeed humans have long looked to the stars and wondered about our origins and how everything came to be. Indeed, I'll tell you that our origins are very linked to the stars, but in some physical, in some cosmic way. We learned, you may have heard, about 100 years ago, the astronomer Hubble found, he measured the speed of various galaxies, various distances away from us, and he found that on average, all of the galaxies he looked at were moving away from us, and in fact, the farther galaxies were moving even faster away from us. The universe seemed to be expanding away from us. Thankfully, already earlier, some 15 years earlier, Einstein had introduced general relativity, which is the correct framework for us to understand that physically what's going on is that in this general theory of gravity, general relativity, space itself, distances themselves are dynamical and can change with time, and the explanation of everything seeming to move away from us is not that we're in some special place, but in fact that over time all of space is expanding on large enough scales. Every galaxy is moving farther away from every other galaxy. And this means that if we play time in reverse, if we're interested in what happened at very early times, then at earlier times, everything was much denser, closer together, and correspondingly much hotter. And this is good. So this is fantastic and is what ties together particle physics and cosmology. When we look at very hot environments like existed in the very early universe, the high temperatures break apart the sorts of matter that we see today. This is familiar at some level from just everyday materials like ice, like water. If you take ice, it's some sort of crystalline solid. Everything is, all the water molecules are attached to each other. If you turn up the temperature, eventually this melts into water, some amorphous, some water molecules that are not as tightly attached. You turn it up even higher, go to something like 100 Celsius, and you find that the water molecules are no longer attached to each other more or less at all. You have produced some gas of water vapor. If you keep turning up the temperature, then another few orders of magnitude at something like 100,000 degrees Celsius, you'll find that you break apart the atoms of the water molecules. You just have separate electrons, separate charged electrons and positively charged hydrogen and oxygen ions. This is what we call a plasma. If you go even higher, you will break apart even higher temperature, something like 10 to the 11 Celsius, an enormous temperature, but you will then break apart the very nuclei that make up the oxygen atoms into their separate nuclear neutron and proton components. If you go even hotter, something like 10 to the 13 centigrade, you'll find that those neutrons and protons break apart into their constituent quarks and the gluons that hold them together, something we call a quark-gluon plasma that only in recent years have we been able to create in the lab. But the universe does it for us. Going back early enough, and when things were dense enough, hot enough, we find that the universe itself was at these enormous temperatures, and the constituents that we can talk about at that time were these incredibly small quarks and gluons. So the details of microscopic particle physics become relevant to the large-scale evolution of the universe and control how the universe evolves, which makes for, I think, incredibly interesting area of study in the early universe of particle cosmology. And indeed, if we go back to times something like a micron after the Big Bang, everything was incredibly hot. We had our nuclear matter was in the form of a quark-gluon plasma. Everything is interacting with each other very quickly. So the interactions are happening so quickly that if you tried to form something like a neutron or a proton, it would get blasted apart by the heat. There are, I should say, also electrons and photons and neutrinos around. I'm just focusing on the nuclear sector. And the universe at this very early time is essentially homogeneous. It looks the same everywhere, very unlike what we see today. Now, at a time like a tenth of a millisecond, finally the universe dilutes and cools and is cool enough that bound states like single protons and neutrons can form. And so the universe at this time looks like lots of protons and neutrons and electrons and photons, some charged plasma. But again, space continues to expand and dilute and cool, and after a more human-sized time, like 5 minutes or so after the Big Bang, you have nuclei begin to form. The neutrons and protons can find each other and stably undergo nuclear fusion, to create from just a single protons up to helium, which has 2 protons and 2 neutrons. This nuclear fusion produces lots of photons, energy as well. And you might ask, so here in the very early universe, at something like 5 minutes, we're undergoing nuclear fusion. We started just with protons and neutrons. The big question is how we get up to today with all of our very complicated atoms. And you might think maybe nuclear fusion continues from hydrogen to helium, and very early in the universe produces all of the nuclei we know. In fact, that doesn't happen. Helium is essentially the heaviest nucleus produced. Well, for one, things are still expanding, so it's becoming harder and harder for different nucleons to find each other and do nuclear fusion. But also, there's this curious fact of the Standard Model that although the proton is stable, the neutron by itself is not stable. So that puts something of a clock on how long this nuclear fusion can last. Because after something like 10 or 15 minutes, all of the neutrons have decayed back to protons. You don't have any neutrons around to perform more fusion to get heavier elements. And you end up with a universe that is around 3/4 hydrogen by mass and just 1/4 helium. This is all still ionic. It's much too hot now for atoms to form. So you have positively charged hydrogen and helium nuclei and negatively charged electrons and lots of photons interacting with them very frequently. But we don't have, at this earlier time, any of the elements, the heavier elements that are essential to our everyday lives. Now, so that was at the era of around 5 minutes. For a very long time, it is still very hot, but gradually the universe is cooling more and more. After something like 380,000 years, the universe finally cools to the point where atoms can stably form, where you no longer have a charged plasma. And since photons are the force carriers of electromagnetism, they interact very frequently with anything that's charged. So in this early stage of the plasma, photons are interacting all the time. But finally, after almost 400,000 years, the universe becomes more or less neutral. All of the electrons and protons and helium nuclei can find each other and pair up to form neutral atoms. And then finally, with the universe no longer in a charged plasma state, you can have photons that can travel for a long distance now without hitting anything. And in fact, we have photons from this era known as the era is the era of recombination. We see photons known as the cosmic microwave background all the way from a few 100,000 years after the beginning of the universe that have traveled continuously and not hit anything until they hit perhaps your old TV set. And really, these CMB photons are a component of the white noise that you'd see on an old TV. And more so than just being an annoyance on your TV, we can build telescopes like the Planck telescopes and map out what the cosmic microwave background looked like to get some information to find what the universe looked like billions of years ago, very soon after the Big Bang. This is a picture from the Planck telescope. What they're plotting here is really the small deviations in the temperature away from the average. Your zeroth order conclusion is that things are still very homogeneous, but you have these 1 part in 10 to the 5 inhomogeneities, and understanding precisely the statistics of what these inhomogeneities, these hotter red parts, these cooler blue parts look like. You can learn a lot about the particle physics of the charged plasma that came before this, and about how gravity is working to try to bring things together and to form bound states of gravity. But mostly things are still homogeneous. Getting actual inhomogeneities happens very slowly over now hundreds of millions of years, let me try to just have in the background this nice recent Japanese simulation of the universe starting out in a relatively homogeneous state and ultimately collapsing to form galaxies. And now there's a surprise in the way this works. The sort of matter that we are made of, this standard model matter, we know that it interacts with itself a lot from, for example, electromagnetism, or just from our everyday lives. You can't put your hand through some solid object because we all interact with other standard model matter a lot. And this means that our type of matter has some pressure. It's hard to compress. It's hard to make it collapse into bound objects. It turns out there is an additional component to the universe that we call dark matter, that we'll talk more about later, that unlike our matter, barely at all interacts with itself, doesn't have any pressure, and so it can collapse gravitationally. I can put this back to the beginning because you might miss the first slides. It can interact gravitationally and fall in to collapsed structures like galaxies far more easily than our standard model matter. So it's this dark matter component of the universe that really controls what things look like on very large scales. And as we play the universe forward, as this all goes, that's not the forward. There we go. As we go forward, some regions of the universe, after something like 100 million years, become so dense and so hot that we're, again, back to the temperatures of the very early universe where nuclear fusion occurred. And you start seeing processes where hydrogen atoms, protons, are fused together to produce helium again, and lots of light and neutrinos. And the light from these nuclear fusion processes provides a pressure against the matter that is undergoing some gravitational collapse, trying to collapse on itself. The light from this nuclear fusion supports these objects of standard, let's do questions at the end, objects against collapse. We have, after some 100 million years, stars, which of course as a byproduct produce all of the light that we rely on Earth. And so finally we have in the universe, after some 100 million years, another opportunity to produce heavier elements through nuclear fusion. But still at this stage, we're only producing helium. Well, and also, whatever we're producing is trapped in the center of a star. But it so happens, that eventually one of these early stars burns through all of the hydrogen fuel that it is using to fuse to helium and starts to fuse heavier and heavier elements, carbon, oxygen, eventually all the way up to iron, which is in some sense the most stable. And finally, toward the end of the lifetimes of these stellar objects, they explode in the form of a supernova and release all of these heavy elements back out into their galaxies. Now, the sun was not one of these first stars, because then everything around the sun would only have been hydrogen and helium. The sun came billions of years later out of this graveyard of supernovas that had produced heavier elements, and so the sun was able to form with a planetary nebula that made planets out of all of these heavy elements, all of the things that we are made of, finally to produce an environment like we see today. And I don't have time to go more into, indeed, the formation of the sun and the earth and all of the interesting geology and the beginnings of, well, now in some time reversal, the development of cells and eventually biology, culture, us. But I think that just even up to this picture of understanding the origins of all of the heavy elements in our bodies in this room from the center of stars some billions of years ago, where they were created through nuclear fusion, I think even already at that level, I want to say again that it's important to understand how the world works. We all make lots of decisions every day, personally, on a collective, on a societal effort level. And I think it's very easy, all too easy, to have those decisions ultimately be based on some stories that we were told when we were children about how the world works that aren't actually borne out when you carefully observe the world. I think very generally, if we want to figure out how to organize a society, it has to be important that for us to properly understand the situation we're in, that we're social primates comprised out of cells composed of atoms, some physical objects that were forged in the center of stars, that we live on some planet that has some billions-year-long complex history from physics to geology to chemistry to biology to culture. But more so than some collective message, what I want to leave you with is more personally is that you yourself are a physical system. If you hold your hand in front of your face and look at your hand, I don't just mean the hand that you are looking at, which I think we all agree is physical, but I mean the you that is doing the looking. Your consciousness is a physical system. To me, this is as simple as the fact that we can introduce into your body some incredibly small amount, millionths of your body mass, of some simple compound, and wait for a minute, and your consciousness disappears entirely gone. I think it's very clear from this experience that consciousness is the result of physical processes that can be controlled and affected by some chemicals. I'll remind you, in case what I've said is too euphemistic, we call this in what I would say should be a profound experience, just general anesthesia. So I think very deeply, very sincerely, understanding particle physics is understanding yourself. It's understanding how you work, what you look like on very small scales. And I think that understanding cosmology is really understanding your history back billions of years toward the Big Bang from the center of stars. So that's what I wanted to tell you about today. The organization of the rest of the talks will follow what I've said. Although hopefully I'll take more questions, I'll be more interactive in these next parts. But as a first part, the next few lectures will go more into particle physics and talk in more depth about everything that we are made of, what we look like on small scales, the standard model of particle physics. Hopefully I'll get to talk about quantum mechanics. Part 2, I think, will be on cosmology, again going through in more detail. Our history is back from soon after the Big Bang. And finally, at the end, hopefully, I get to talk a bit about what is really my professional interest, which is in going past what we know, looking at even smaller distances, at even earlier times, trying to understand theoretically what could be beyond these standard models, and what we really look like on a fundamental level. So I hope you'll join me. Thanks very much for your attention.
So Seth will answer questions. I want to say one thing for next time, that I promise we will have more chairs. Please, go ahead. Thanks, Seth.
Yes, some questions.
So going back, we still think that the Big Bang started from a singularity.
I think in a
Or a Planck volume.
in a more complete theory of physics, there shouldn't be any such singularity. Indeed, general relativity predicts that things started from some sort of singular configuration, but we know sort of from that in fact we need to go beyond general relativity. Ultimately, we need to understand how general relativity works with quantum mechanics.
And how did gravity come out of that? Since it wasn't space.
It's a very good question that maybe we'll get to, but I don't have a quick answer. But the topic of ongoing research. Yes, we're over here. Sorry.
Why is that such a masculine compound to say the Big Bang? It just sounds masculine to me. It's not parthenogenesis. It's not parthenogenesis at all.
Name Fred Hoyle.
Now, do you know what parthenogenesis means?
What sure, virgin birth, something. If you like.
Parthenogenesis?
Yes.
It's like Athena born
Out of Zeus's
Mary,
head.
Virgin Mary.
Sure, yes.
Immaculate Conception. Why is that so masculine? And what brought about this masculine Big Bang? I mean, masculine in my concept. There's a historical and linguistic question. The term Big Bang, like many terms that have caught on, was actually created by critics of the theory. Precisely. I'm not sure I really have a good answer to your question, other than to say that I think a lot of how one reacts to such a term is shaped by one's own culture. But yes.
You pointed out
You and I were
about
thinking about the same
dark
thing.
matter.
Mm-hmm.
It seems to have no import in any of the evolution you pointed out in the evolution of
Some BS term that some guy thought of.
the
He
fusion.
hated his whole
Mhm.
life.
And it comes about only a large
There
scale
was no
and
Big Bang.
affects things only
There was
gravitationally.
That's right.
no Bang.
So it's an
No,
aspect.
that's the masculine. It is. It is.
Yeah.
Dark matter is sort of a gravitational phenomenon.
That's right. The only way we know
Is there
dark matter now.
anything about it anymore other than that? Does it pop out of any kind of?
It's a great question. Ultimately, our best theories of dark matter do suggest that it started out having stronger interactions with us, but now in the late universe only interacts gravitationally. But it's an active topic of research, and we've been searching for many years with very precise experiments to try to look for dark matter non-gravitationally. We haven't found anything yet, but it's ongoing.
Does it give you any?
Very good question. Yes.
I've got two questions.
Okay.
Okay. Number one, you indicated just in the analysis, the way scientists are looking at things, there's no magic. You made that statement. And I would say there is some magic, and I'll give you one example. You take two human beings, one's alive and the other is dead, and you incinerate both of them. The elements that are there are most likely the same,
Sure.
okay? But one has life and the other one does not. So the mystery of life is magic, even in the area in which you're doing work. That's my first question. Okay, and number two, I'll
Okay.
get my questions out and you.
Sure.
Okay, you talk about the Big Bang. I perceive that takes place in a small place and it expands. And you're talking about the universe expanding. What seems mysterious, magical to me, and I can't understand, is if the universe is expanding, is what's in the universe itself, that box or that globe, is that expanding, or is what the material things that we're talking about in the universe, are they expanding into something? I have a difficulty conceiving infinity.
Sure.
If the universe is constantly expanding, is it something physical.
Sure, sure, I understand.
Okay,
Thank
I'm
you.
through.
Good questions. For the former, I'll say I disagree. Indeed, I was raised myself as a vitalist to believe that there was something fundamentally different about the chemicals that were in a living being and those that were artificial or in something that was not alive. I don't think that's correct. We can understand signs of life based on these cellular, in our bodies, these cellular properties. The living person has red blood cells that are carrying oxygen to different cells. It has neurons that are still firing in stable ways. So we understand now what life looks like on a cellular level. We can understand even what life looks like for a single cell. Maybe next time I'll play some more videos about some microscopy. I think with today's technology, indeed, we can understand in a really profound way how cells work, what makes a living cell. The question about in conclusion, I think I disagree, although I understand that I understand where you're coming from. Indeed, the question about distances expanding is a very good one. It's true, infinity can be hard to picture, but indeed, what you should have in mind is not that the universe started from some single point and expanded into some larger volume, but indeed that the universe has always been infinite. What happened, the way things were in close to the Big Bang is that everything was closer together, but in fact, still infinitely large. As the universe goes forward, you have still an infinite plane, an infinity of space, but indeed distances, the plane itself is expanding. So there's nothing that it needs to expand into. But good questions. Let me go back. Yes. Sorry, I'll get to you next.
Your lecture being so broad has provoked a gazillion questions, but I'll limit myself to two.
Okay, thank you.
The first of which can be answered in a single word, but is probably burning on everyone in this building's mind.
Perfect.
And that is, how do you say the name of this building correctly?
Michelson, I think?
Okay.
Michelson, yes.
The second one is, so you're talking about a physical view of everything, ourselves.
Yes.
Okay, including consciousness. Have you given any thought towards taking that even further in this sense? So to me, observationally, you are a pile of protons, neutrons, and so on and so forth.
Sure.
And vice versa. And I have always considered it to be a philosophical proposition that everyone undertakes, whether they know it or not, they are philosophers, to ascribe to the other the same subjective consciousness that I experience myself.
Yeah.
And I ascribe that to you, otherwise I wouldn't be talking to you.
Yep.
And vice versa there too. So have you given any thought to taking what you've said about everything being physical, including consciousness itself, another step beyond that and say, what about this idea that I'm sort of projecting on you, on every other human being, my own subjective experience of my own consciousness?
Sure. Yeah. I think that's an important thing to think about. I think indeed the most parsimonious explanation is that other people work the same way you do, and you can think about that operationally, but you can also think, I suppose, more physically, that there is some unbroken chain of ancestry between you and I. We shared a common ancestor, something like 100,000 years ago. We know that we work on some very fundamental level very similarly. So indeed, I think the based on our understanding of biology, the processes that occur in my brain should be quite similar to those that occur in your brain. Although it's easy to, it's interesting to also think about, consciousness is a messy thing. People's consciousnesses work differently. Not everyone has an inner monologue. Not everyone has a mind's eye. So on sort of a double-sided answer. Indeed, yes. On very general grounds, I think it's very well founded that we are mostly the same. It's also very interesting to understand the differences of our internal lives. I promise. Next, yes.
Are there other Big Bangs? Is this one single Big Bang that happened in the space? How about in other location? Is it possible that another Big Bang happened?
Good.
Yes, it's just one question.
Yes.
Another one is, do universities allow somebody to really come up and prove that Big Bang did not happen? Is there any university that would allow this thought to really contradict that Big Bang, there is some alternative to this universe?
Sure.
I'm gonna give 10 seconds to think about it.
Thank you. Good questions again about whether our Big Bang was the only one. It's a topic of active research. We know that all of the objects that we can see in the universe out to enormous distances like 80 billion light years, all of this originated with one Big Bang, all of our observable universe. It's a question, maybe something that I'll get to in this last part. It's a question about what happened at even earlier times, whether the Big Bang really happened everywhere uniformly throughout the entire universe, or whether maybe it happens in different ways at different places.
Two or three Big Bangs.
So in terms of everything
At
that
the
we
same
can
time, not one after the other. At the same time.
I don't see the
And why not?
Big Bang really here refers to the beginnings of when we had a very hot, dense soup of matter. But indeed, as you asked, as you're suggesting, people are asking all sorts of these fundamental questions, including some very some very preeminent cosmologists who indeed are questioning whether the Big Bang happened the way particle physicists have in their minds at all. So absolutely, I think the field of cosmology and particle physics are very healthy in this regard. There are lots of dissenting or people who do research on dissenting ideas, alternate frameworks. Everything that I've presented, you'll notice I didn't really try to go into the Big Bang. Everything I've presented, we understand very well theoretically and also empirically. We've really confirmed everything that I told you. All of these further questions beyond the standard model, earlier times, there are lots of voices. You indeed see lots of research coming out of universities on all sorts of different angles. Absolutely. I think there was a question over here, if we can, sure.
It's basically what these three gentlemen, and I think this gentleman too, it seems like life is an emergent property. You know, you've got all these things, but then it's something that you just can't basically chart, that there's certain things that just emerge on the basis of just having other things there. But my question I wanted to ask is, in terms of the question about gravity, And I know you wanted to kind of defer that to later, but what really came first? A luminous universe or a dark matter universe? In other words, did the a luminous universe form first in an environment of dark matter?
Good. It's a great question that we don't know the fundamental answer to. In many of our theories of dark matter, first, the standard...
Yes, because the virgin universe that formed, or the Big Bang, you want to call it, it seems to all the constructs explain the formation of luminous matter, but it says nothing about the formation of what dark matter.
Good. So the minimal version of this theory that I presented only about the stuff that makes us up, indeed, it's just about that. We do have, it's a very active topic of research about exactly how dark matter fits into this picture. Indeed, in some versions of the theory, and we don't know what's correct yet, in some versions, the standard model stuff, luminous stuff, came first and produced dark matter. In some models it was the other way, in some models they were both produced at the same time. So it's a question we don't know the answer to. But I'll say also briefly, we're understanding better and better precisely the origins of life. The University of Chicago at the beginning of this past year hired a professor who won the Nobel Prize in biology, Jack Sostak, in a building a block over there. He has a lab where they're doing some really fantastic work finding cell membranes, this basic ingredient of life, come to existence out of some primordial soup of definitely non-living materials. So it's something, indeed, we don't have all of the answers yet, but it's something we're getting in closer and closer to, including here at this university. All the way in the back, yes.
First of all, you got a great head of hair.
Thank you.
It's going to be online or they're being recorded.
Yes.
And do you want to say, they are?
Yes.
Good. And do you want to say anything right now about cold fusion? Are we getting closer?
Oh, good. So the lectures are being recorded. They will be put online on the EFI website.
Yes.
Cold fusion is certainly not my area, so I don't have anything to say on the. It's more technological. I'm more of a theoretical guy. Maybe a couple more questions. Yes.
One more.
One more question.
One more question.
But then I'll continue. You can come up and chat. Yes.
Thank you. This is a question I asked of before the shutdown of the Compton lecture.
Okay.
A couple of others, and I'm not sure I got a good answer. Back in 1964, when the Higgs field was first hypothesized, did they have to understand back then that there was such thing as dark matter? Because that's gravity also. And one more, when they be detecting the boson at CERN, did they have to understand that maybe the Higgs field did have some influence over dark matter as well as regular matter?
Good question. Indeed, the Higgs field has something to do with how we interact with gravity, but this really is, at least in general, a very separate question from dark matter. The Higgs field is part of the standard model. It interacts with all of us very frequently. This is very different from dark matter, which is something that, aside from through gravity, doesn't interact with us almost at all. So no, we barely understood dark matter at all in the 60s. And even for understanding, for finding the Higgs boson, we didn't need to account for dark matter at all in finding it at the LHC. Okay, I think that was a great question. Thank you.